All right, we're good.
Okay.
All right, hello. My name is Cameron Cogburn, and I'm from RPI. I'm going to be talking to you right now about the quantum simulation of the Spin-Boson model. This is done in collaboration with my collaborators here, also at RBI and IBM. All right, so what's our motivation? Well, the Spin-Boson model is a system of interacting spins and bosons, and it can be used to model a variety of physical systems. So some just examples of this are quantum impurities, a single spin with many bosons, superradiance, a single boson or cavity mode with many spins. It can also even be used to model noise in quantum computers, the entanglement between a qubit and its environment. So the motivation of this talk in particular is that we want to faithfully simulate and calculate observables of this quantum spin boson model at a utility scale using new techniques, of which I'll explain to you shortly. All right, so let's be specific. So what is the spin boson model Hamiltonian? So I'm going to be speaking about a system of N interacting spins and M bosons that have P occupation levels. Now, what do I mean about P occupation levels? I mean that in reality, there's a continuum of bosonic modes, but to model the bosons on either a digital computer or a quantum computer, we need to provide a truncation at some point. All right, so that's what I mean by this. That's what I mean by this variable P right here. All right, so let's go through the terms of this Hamiltonian individually. So this first term here, this is just the spins, okay? This middle term here, this is just the bosons, the bosonic modes. Now this final term here is the coupling between the spins and the bosons. And the coupling parameter in particular that I'm gonna be speaking about today, and some of the plots you'll see, is G. Okay. So there are three natural observables to this model. Right? The first is just looking at the spins, such as their average magnetization. Another one is looking at the occupation number of the bosonic modes. That's just the average occupation number where the bosons are. And the final one is we can, of course, look at correlators, the correlation between two spins in this model. Okay. So how do we map this to the quantum hardware in particular? All right, so I mentioned earlier that we have some truncation of the bosonic modes such that we can do that. So suppose we have little m total bosonic states. So there are two established strategies to map this to the quantum hardware. The first is so-called unary encoding, and it's pretty simple. It just says that if there are little m total bosonic states, we will need little m total qubits to, simulate these states, right? This is in contrast to binary encoding, which is what you may intuitively think of when you think about modeling a spin system on a quantum computer, where you use just one qubit for one spin to represent, say, the up and down and the computational basis. All right, so why do we want to do this? Well, in terms of qubit number, unary goes as order m here, whereas binary goes as log m. Okay, so you might think, okay, binary is more efficient in terms of qubit number. However, in terms of gate number, which is also a proxy for noise, unary still goes linearly in m, but binary goes as m log m. So especially as we look at larger and larger bosonic modes, unary encoding is going to be vastly more efficient in terms of noise. Okay, so what's the algorithm we're going to use to calculate ground state observables and the eigensystem here? We're going to use the so-called sample-based quantum diagonalization method. Now, this is a method that was come up with by Javier and some of his other collaborators in this paper down here, and he's going to be giving a talk in this room on Wednesday morning, specifically on this algorithm, all right, in detail. But I'm going to try to go through it a little bit on this slide. So the main strength of this algorithm is it's a post-processing technique that acts on the noisy quantum bit string samples to solve the eigensystem. So kind of getting back to a point that Bill alluded to in his previous talk, we want to use some algorithm where noise is an advantage, okay? So that's one thing about this algorithm that's unique. So to be very clear, the input are bit string samples and the output is an estimated ground state energy or eigenstate or ground state observable, right? So how this works is as follows. The first step is to collect the noisy quantum samples into a bit string matrix. We do this using a time evolution circuit, which I'll talk about on the next slide. The next step is to refine these samples based on some sort of criteria about the system. In this case, we're going to mandate that, of course, the bit strings need to have the correct bosonic Hamming weight, right? If it has the incorrect Hamming weight, it's not a physical state, we can just throw it away. The third step is we're going to collect batches of these samples to create subspaces to find the ground state in. All right, and this is really where classical post-processing comes into play. You could parallelize this step on a supercomputer, so on and so forth. There's a fourth optional step where you could further refine the samples based on the results of step 3. I don't want to get too much into the details of this, but it's something you could conceivably do and refine the samples further before repeating the entire algorithm again. All right, so let's actually do this for the simplest non-trivial system we can think of. 2 spins and 1 boson with 2 states. All right, so this is how we're going to map it to the hardware. We have our spins here in blue. They're binary encoding, so they just require 2 qubits for 2 spins. This 1 boson with 2 modes, it's unary encoding, so it requires 2 qubits, 1 for each of its modes. So how are we going to generate our samples? We're going to do it using a time evolution circuit, okay? So basically, we use this time evolution circuit, and at the end, after running through this circuit with many different couplings over many different time periods, we perform a measurement, and this is how we create our samples, okay? All right, so what's the hardware that actually does this? So we're very lucky at RPI. We have an IBM System 1 Eagle processor right on our campus. It's actually in the chapel. And so that's how we generate our quantum samples here. We also, for potentially the post-processing step, we have a IBM supercomputer as well that, in fact, we have also set up, not for this project at least yet, to be able to work in a hybrid workflow with the QPU. All right, so that's also another reason we're pursuing this SQD algorithm. All right, so what's an observable that we can look at? We have a time evolution circuit, so let's just look at the dynamics of some observable for fun. So let's look at the occupation number, for example. So the initial state here, we're going to start with excited spins, but the boson in its ground state. All right, and what you're going to see here is that dynamical decoupling is key to data fidelity, at least for this observable in this time evolution circuit. All right, so for no coupling at all, G equals 0, we're in the ground state for the boson, and so we're looking again at the number occupation, and it stays at 0 for the simulated data and also for the QPU data. Now, as we turn on the coupling here, now G is equal to 4, we start to see some dynamics, right? As you can think of the energy of the system kind of sloshing between the spins and the boson. Now, interestingly enough, as we really start to crank up the coupling, we see here at first that if we do not have dynamical decoupling on, we start to see some corruption of the data. All right, so we expect the oscillation to come fully back up and down, but it doesn't. And actually, as we crank it up more and more, we see more of this corruption. Okay. So I don't want to harp too much on this. It's just an interesting thing that we noticed. All right, so let's talk about the convergence of the eigensystem. So again, we use a time evolution circuit to generate our quantum samples, our noisy quantum samples, of which we're going to use this algorithm to solve the eigensystem. All right, so if we do this with the simulated data here, we get a plot like this, okay? We see at first some oscillations and then a convergence to an estimated ground state. If we do it for the QPU data, we see something very similar as well. All right, so, okay. So that was for a small system. What we really want to do is to simulate a utility scale experiment. What I mean by utility scale is tens to hundreds of qubits, all right? So to do this, we need to map to the hardware in a way to minimize swap gates, to minimize noise. So the strategy is to construct hardware-friendly Hamiltonians that do this. So one example of this might be this type of configuration, looking at a system of 6 spins and then 1 boson with 11 modes to it. And so you can see, obviously, for the modes, the bosonic qubits here to touch all of the spins, we're going to need some swap gates, but we're not going to need nearly as much as if you were just to naively, paste this onto the hardware in some snake-like line. Okay, so that's what I mean by constructing hardware-friendly Hamiltonians. Okay, so we're actively looking at things like this and other configurations, and hopefully in the near future, we'll have results for these experiments to report on. So thank you for your time.